This is a very unusual evening, and we have indeed an unusual attendance. I would like to welcome His Excellency Sir Ophir Akunis, Israeli Minister of Science, Technology and Space, His Excellency on his way, the Israeli Ambassador to Switzerland in Bern, Sir Coker Idan, and Her Excellency, the Israeli Ambassador to the UN, Mrs. Aviva Rashechter. We are truly honored to have you with us tonight. As I said before, this is a very unusual event, an experience for most of us. On the one hand, we have Professor Idan Segev, one of the top scientists in the world involved with brain research. On the other hand, thank you. On the other hand, we have Mr. Paul Coker, a fabulous musician who has been collaborating with Yehudi Menuhin for more than 10 years. So we thank you both. I thank Idan because he came all the way from Jerusalem to be with us tonight. And I thank Paul because I think he accepted the challenge of a conversation with Idan, and it's a challenge. Together, they will try to let us discover how the brain of a musician is actually working. But before I step down, because I'm going to be very short, I would like to address particularly to the young generation. The young generation who is probably with us maybe for the first time, thanks to the involvement of our outstanding new collaborator, Farah Savdiye Yarisal. We need you. We hope you will quickly discover all the extraordinary projects and research that is done at Hebrew U. I hope you will go there and see by yourself. Sorry, that's getting too small for me. I hope you will enjoy this evening, and I would like to invite His Excellency, the Minister, Israeli Minister to Science, to come on the stage. Thank you.
Thank you very much, and good evening, shalom, לכולכם, ערב טוב. Mrs. Gilden Efrati, President of the Swiss Friends of Hebrew University, Professor Idan Segev, Director of the Department of Neurobiology at Hebrew University, Mr. Paul Coker, Mrs. Ambassador Aviva Rashechter, Ambassador Coker Idan, he will be here, distinguished guests, ladies and gentlemen. I am delighted to be here in Switzerland to address you all on the occasion of this beautiful conference, The Brain of a Musician. I must begin by informing you that I am very interested because ever since I was young, I loved music and listened to a lot of kinds of music. It's very interesting to be inside the brain of a musician. I wish to convey on behalf of the Israeli government and the people of Israel my very best wishes to this special occasion, and I look forward to what will be discussed later on tonight. But before, I would like to ask you a question. Why is Israel called the startup nation? Why? I will answer, don't worry. What is our secret that gave us, a small young state, this name? Well, I will tell you. We have one high levels of technological knowledge. 2, a great deal of creative thinking. And 3, a huge motivation to succeed. That is what encourages Israeli children to dream big and grow up in a highly creative environment. This is what makes Israelis proud to call themselves an Israeli. And this is what makes universities and organizations around the world want to work with Israeli organizations. The Hebrew University of Jerusalem was founded in 1918, 30 years prior to the establishment of the State of Israel. It is Israel's oldest and leading university in the field of mathematics and science. And by the way, it's 2 minutes from the Ministry of Science in Jerusalem. 2 minutes. We can walk from the ministry to the university. And it's a beautiful place. And in the other side, by the way, the Hebrew University, in the other side of the city, it's 2 minutes from the Prime Minister's office and from the Knesset, the Israeli parliament. Good places. According to a study by the Academic Ranking of World Universities, Hebrew University was ranked 33 in the world for study in the field of mathematics and 51 in the field of science. And Hebrew U continues to work on brain research, which is a topic we will be discussing, all of us, later on tonight, and one which is very important to the research being developed here in Switzerland. I commend the staff and the leadership of the Hebrew University for their outstanding work to achieve this ranking. I would also like to commend the students for their hard work and accomplishment in the technology of tomorrow. The students of today will be our leaders of tomorrow. They are our future scientists, teachers, doctors, lawyers, and as I said, the leaders of tomorrow. They have the passion, energy, and the commitment to make a difference, not only in their respective countries, but rather in our shared world. Due to an increase in the ministry's budget, which I can say is the largest one yet, we can fund new programs, increase community engagements, science and innovation in our efforts to develop the leaders of tomorrow. And I want to give you one example because I have a very short time. So I will give you the example. The Science Basket is a governmental program I initiated that allows municipalities in Israel to tailor their science offerings to the needs of their citizens. They can choose which area to focus on: space, robotics, cyber security programs, chemistry, or many other fields. Generally, as you know, Israel's contribution in the fields of science, research, education, and in improving the world throughout Tikkun Olam could not have been possible without the help of the diaspora communities, including you, of course. Israel could not have earned the title of Startup Nation without the hard work of the Swiss Friends of Hebrew University, without you. By signing a strategic partnership in the field of science with the University of Geneva in 2016, Israel's high level of technological knowledge, creativity, and motivation can now take on a role of creating bridges with local institutes and populations around the world. So I'd like to say thank you. Thank you for supporting Israel. Thank you for standing with Israel, and thank you for participating with Israel, the Startup Nation. Thank you very much, and greetings from Jerusalem.
Thank you everybody for coming. You enabled us, Paul and myself, to have an unusual evening, and for this I want to thank you. And I think you will enjoy this evening. I just want to very briefly to tell you what is expected. It will be an hour and a half, so you will be free at 9 o'clock, I assure you, unless you want to ask us a lot of questions, which we are most welcome to do, of course. And so the evening is built between us as follows. So Paul will start with a piece of Scriabin, left hand. Then I will give you a 15 minutes or 12 minutes talk about the frontiers in brain research worldwide, focusing on this unique center in Jerusalem that we are now building, the Edmond and Lily Safra Center for Brain Sciences. So this will be a general introduction and exposition of the challenges we have in brain research, focusing on some recent highlights, but it will be very brief. All the evening will be relatively brief. Then Paul comes back and is going to play two hands piece, and later on we shall discuss myself about his particular brain. So Paul has an unusual brain, not only of a musician, but a special brain of a musician. He didn't play on stage for the last 15 years. It's his first reattempt to play again, and for this it's really a unique event for him and for me. I heard him personally, but not on stage. And then we should discuss the brain of Paul, which is a very special phenomena. I'm sure he will learn also about his brain from my talk about his brain. And you will talk about the brain of a musician in general, but as particular phenomena that is not as unique as you will hear. It's a very particular unique phenomena of musicians and especially of pianists. Something unique about the brain. But I leave it open for you. This will be another 15 minutes. Then Paul and myself will discuss with you whatever you want to ask, whatever we want to discuss for about a quarter of an hour. And finally, Paul will give you the left hand Chaconne by Bach. So that's the plan for the evening. So, Paul, it's your turn.
Scriabin. He could have written it like that, like a normal piano piece, but he chose to write it for only the left hand alone. And maybe this piece illustrates why the piano is an instrument of illusion, because what we call legato, or joining notes together, that violinists can do so naturally and singers also. On the piano anyway, even if you have two hands, is an illusion. And later on in this piece is in two parts, a prelude and a nocturne. The nocturne starts like this. But when you play it with one hand, as it's written, your ally is going to be the pedal, of course, and if I don't use the pedal, what I'm doing with my left hand is actually this. There's the illusion. So, Prelude and Nocturne for the left hand by Scriabin.
We have to discuss later what makes in music, what is in music that ignite emotions so fast, especially when you play it. Wonderful, really, Paul. After 15 years of not playing. Okay, so let me start, of course, with one we cannot start without, is Einstein. And he was saying something important. You know that we came here without choice. We are here, not in Geneva, in the world. But he said the following, which is really related to what we just heard. There are two ways to live our life. One is as though nothing is miracle. The other is as though everything is miracle. Certainly music is miracle, science is miracle, and I want to discuss with you some miracles. And especially what we do in Jerusalem, but worldwide, we should discuss later our collaboration with Geneva. So the plan is as follows. I want to really discuss a little bit about frontiers in brain research, something to say about our own brain. You know that we have unique brain among the animal species. It's a very unique brain, especially the creative aspect of it, also the problematic aspect of it, but we can discuss it later in many ways. I want to discuss ELSEC, so this is the Edmund and Lily Safar Center for Brain Sciences that we are just building now in Jerusalem, due to the huge donations from the Swiss, not only, but mainly from Switzerland. I want to give you some examples of what we do. I cannot discuss all of it today within 15 minutes, but I want to discuss especially breakthroughs in understanding what makes us remember. What is changing in the brain when you remember. So I hope you will remember this evening, the Scriabin piece, and the rest of it. And I want to tell you what happened to your brain after this evening. It cannot be the same brain. If it will be the same brain, it will be terrible, because that means that you didn't remember anything. So nothing happened. It cannot be the same brain. So physically, the brain must be changing through learning. And of course, in some diseases, it does not work anymore, like in Alzheimer's. So I want to discuss memory. I won't discuss, but we are working very hard in brain and stress. This is a very stressful world. I want to discuss very briefly Parkinson, but I don't want to discuss diseases necessarily, because the brain is wonderful without diseases, but we have to fix diseases, and of course this is my role as a scientist, to find ways for diseases. And I want to convince you at the end that we need to model the brain in the computer in order to understand this. This will bring us to a new era of intelligent machines, which we are approaching very fast. But we can all discuss it later on the table. We have time. We can stay here until 11, but we shall see if you want to stay. And then I want to discuss very briefly what makes our brain unique. What is it different between my brain and your brain than, let's say, of chimpanzee? And of course, then we have to discuss creativity, our emotions through music, for example, consciousness. I'm aware that I'm talking in front of you, and so forth. This is not for this evening, but this is topics that we are dealing with in our new center in Jerusalem. But just to remind you where you came from here. So it started there, actually before, but in the last 200,000 years only, very, very briefly, we live as a species only 200,000 years, the Homo sapiens. And during this period, which is this yellow region on the line of years, so about 200,000 years ago, there is a new species, the Homo sapiens, and genetic change that brought us here, the Homo sapiens. There were hominids, like the Neanderthals, at the same time like us. You know that in south of France or in Africa, there were Neanderthals together with us, also homo types, but not Homo sapiens. They disappeared. We govern the world. We are the only Homo species living today, as much as we know. We don't know of any Neanderthal living somewhere, but we know that each one of you has genes of the Neanderthals. I have 3% gene of the Neanderthals, because I made a check. But you can check it also, if you are interested to know. The interesting thing is that it means that 200,000 years we are the same species, with the same genome on average. Of course, my genome and Akuni's genome is not the same, but we are the same species, so there are variations of genome, but we are the same species. But during this genome, without any change in the genome, we continue to generate new things. Language and mathematics, science, modern computers, cell phones, and science, understanding the brain. So this is a very new phenomenon. The whole field of brain research is only 100 years old. the systematic attempt to understand the brain is very, very recent. It's with the same brain that already lived here 200,000 years old. So we could also start to understand the brain 200,000 years ago, but we did not. So that's the beauty of the human brain, is this capability to change the world physically, to build things, to believe in things, to create things, and through this changing of the world, your own brain is changing, and we should discuss it in a second. So this is very unique to the human being. There is no other animal that generates new things all the time. Like the monkeys or the chimpanzees are doing the same thing for already 8 million years. They don't change. They do the same thing. They don't learn the new things. They do the same thing. But we do new things all the time. And that's, of course, a big challenge to understand what is unique about our brain. So I'm not going to discuss it, but I just want to show you your own brain. So this is a simulation that I'm doing here in Geneva with Henry Markram and myself. I'm part of this Blue Brain project here in the Geneva Biotech. And we are simulating pieces of brain. This is a cubic millimeter of a brain, just a cubic millimeter, which is very, very small. You can see the jungle in your brain. It is composed of nerve cells, a lot of wires. Just to give you numbers, so within 1 cubic millimeter of your brain, 1 cubic millimeter, it's a very small, like a pinhead of a very small thing. You have 4 kilometers of wires, you have 100,000 of cells, and you have about 40 million connections, synapses. So we need to understand how this piece of brain is doing all that it does, including playing piano by Paul Coker, or speaking here now. And in order to do that, and that's the big challenge of our center and many centers in the world, is to try to link what we know about the mechanism of the brain, what we call the neurobiology and the medicine, the elements in the brain, the physical elements in the brain, how these physical elements that you just saw part of them is generating behavior. So I'm behaving and you are behaving, but it is all due to these physical entities, and we don't understand how these physical entities generate behavior, love, feeling, beliefs, creativity, and so forth. And in our center, which is now a model of many other centers in the world, we realize that in order to make the link between the mechanistic part of the brain and the behavioral part of the brain, we need theory. We need a mathematical model of the brain. Otherwise, we won't be able to make the link. So in order to make the link, this particular link, we are building a new center in Jerusalem. So this is the Jerusalem Brain Center, built by Lord Norman Foster just now. It looks like this. It's really now being built. So in front of my office in Jerusalem, I see this building, and this is my office, you see here. And this screen is reconstructed by Lord Norman Foster. It's a patent. Designed by myself, by the way, with Foster, just to have a feeling of a brain building. So if you are inside the brain, you will see something like that. So this is a building from within. So this is a lab that you will see outside, and you will be within the brain outside. So we are very proud about this building because there will be 30 new laboratories dealing with creativity, consciousness, Parkinson, and all other things. But the most thing, and Ophir Akunis just mentioned it, in Israel we don't call Mr. or Sir, we are all Israelis. So forgive me for calling you Ophir Akunis. He mentioned this, that this is the future. This is the future, clearly. So this is the young generation of brain research. We call them the Leonardo da Vinci's. So for example, Talia Tron is coming from physics. So her background is physics, but she's dealing with schizophrenia. So a physicist working on schizophrenia is something completely new. Usually physicists do not work on schizophrenia. And you can see many examples, I don't have time to show you. First of all, we are very proud that we have 50% women and 50% men in our very prestigious center. So it's not just as an example. We have 80 PhD students. It's the largest brain center in the world by far. And it's a very, very sophisticated, without going into details, I'm completely in love with this young generation. They don't want to do anything else but to understand the brain, which is already fantastic because they could go to startups and to do a lot of money. They want to understand the brain. So I'm very proud of them, and I think all of us should. Let me give you some hints to breakthroughs. I want to discuss memory. We have new technology, without going into details, whereby I can look at the behaving brain of a mouse, not of a human. We should discuss human in a second, but of a mouse behaving, learning something new, like a maze. So the mouse needs to go from here to there to find the cheese, because he likes this restaurant. So he needs to find the way. And during this exploration, I can look at the brain physically and find out what is changing when the mouse is learning this new thing, this maze. This is a microscope that we succeeded to get through help of friends like in here, because this microscope is a new technology. It's a 2-photon microscope laser, and this is Adi Mizrahi, who is one of our leader, and I want to show you what happens in your brain now when you learn something new. So this is in a living, behaving brain. For the first time ever, you can really see anatomical changes underlying memory and learning. So I want to show you very briefly a little movie here. Hopefully it will work. So these are two pieces of small fibers. This is a fiber of one cell. This is a fiber of another cell in the living brain. And you will see, I will run it again, you will see that there is a new connection, a synapse, a new connection being formed now when the mouse is learning something new. Okay? So look, this is one piece, this is another piece, and you can see there is this little piece, it's 1,000th of a millimeter, 1 micrometer, that is moving, anatomically, physically moving, until there is a new connection. So I'm telling you that in your brain, when you learn something new, if you use your brain, if you do something new, if you are challenged by something new, otherwise no. But if you are challenged by something new, then there is many new connections. I'm showing you only one. So if you learn the letter A, or you learn to play the piano, or you learn what I'm just telling you now, I'm making you a lot of new synapses, a new connection. So physically I'm creating functional networks that are now connected to each other, and they will represent something new in the future if they will be activated. This is one new finding, that memory, what underlies memory, partly there are other mechanisms, but this is essential mechanism, is making new connections in your brain. We also found, this is Adi Mizrahi, I just showed you, that in your brain, if it is challenged by new challenges at any age, so this is an adult brain of a mouse, you can see that there are newborn cells, for stem cells that are being born in your brain. They are migrated to a new location and they become mature nerve cells. We did not know that in the old brain, in the mature brain, in the adult brain, there are newborn cells. We thought that we are only losing cells. No, you have every day 10,000 new cells being born, but they are not going to survive if you are not making use of them. So I'm challenging you to do new things with your brain. Try to play the piano. The other thing I want to show you is another thing that we are doing in Jerusalem, and Haggai Bergman is really a leader, and hopefully the next Nobel laureate, I hope so, in Israel, that is working on Parkinson, and he was the first one about 15 years ago to find when recording the electrical activity in a particular region deep in the brain, it's called the basal ganglia. We shall talk about the basal ganglia when we'll talk about Paul Coker. Because in his brain, doesn't know it, but in his brain, not anymore. There was a little problem there, that made it very hard for him to play for 15 years. So this is the second talk. So remember this basal ganglia. This is the activity of 3 cells. So the cells in your brain are firing electrical activity. Stop. This I mean electrical signal. It's called spike, and this is a normal activity. But in the Parkinsonian brain, Haggai found that when you have Parkinson, the activity completely changes. You can see that the nerve cells are active in a bursty activity, like a machine gun. So, ta-ta-ta-ta, stop, ta-ta-ta-ta, stop, ta-ta-ta-ta, stop, ta-ta-ta-ta, stop. And all the cells in the network starts to fire together. So the whole network of neurons in this region is firing and stopping, firing and stopping, firing and stopping. The output is the tremor, is a Parkinsonian tremor. So this is a wrong electrical code in the brain, And Hagai was the first really to invent this amazing idea that you can stimulate the brain electrically. So instead of taking the battery and pacemaking the heart, he uses the same technology but more sophisticated to pacemake electrically the brain, to inject electrical stimulus directly to the brain, hoping that you will succeed to fix the wrong electrical activity by manipulating this activity directly in the brain. It's called deep brain stimulation. And I want to show you a big success. This is now worldwide. You have it here in Shuv, you have it in many hospitals, but the original idea came from Jerusalem, the deep brain stimulation idea. So here is a patient in the medical school Hadassah. You can see a Parkinsonian patient, and one clear thing that Parkinsonian patient cannot do, and this is always a test I do in the morning to myself to know whether I'm Parkinsonian or not, is this. If I can do this with different rhythms, tak, 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 I'm not Parkinsonian. But he is Parkinsonian because he cannot do it. You will see in a second that the Parkinsonian patient cannot generate his own or her own rhythm because this rhythm is generated by this brain activity. So you can see that he cannot generate his own rhythm because of this disease. Now you do this fast operation, few hours, completely alert. By the way, not every patient enables us to photograph, to video him, but this is after agreement, of course, of this Russian immigrant, 56 years old. So after this operation, and this is miracle, we spoke about miracle of Einstein, you see this guy coming completely tremor. He gets this operation, the deep brain stimulation operation, and he goes out of bed like this. So he's now getting stimulus to the brain, yes? He's getting electrical stimulus to the brain now, but you can see that he's quite amazing. I mean, you really cannot see that he's a Parkinsonian patient. And this is really something, that's why I'm very hopeful that Hagai Bergman will get this Nobel Prize, because this is amazing. See what he does. This is Hagai Bergman, not myself. Okay, so you saw two examples, memory, new cells, Parkinson, and I want to talk about brain simulations. So we have all these diseases, stress, sleep disorders, 350 diseases of the brain we know of, but we don't know how to cure them besides symptomatically, as I just showed you in Parkinson. What do? We need to understand the disease. How do we understand the disease? Here in Geneva, in the biotech, together with our group in Jerusalem, we are building mathematical models, without going into the mathematics, of particular diseases. What happens with this circuit when you get epileptic seizure? What happens in this circuit when you cannot sleep? It's all a manifestation of some difficulty in some circuit. What happened to Paul Coker, who could not play for some time? What happened in his brain? I will tell you in the second talk. So that's why we need the model. We need a mathematical model to replicate this piece of a tissue that we know is sick, but we don't understand why. What is the mechanism? Why this piece suddenly generates epileptic seizure? Why this other piece suddenly generates this wrong code for Parkinson? What happens there? So we want to copy this in the computer. We succeeded to copy a cubic millimeter, as I showed you before. We start to understand diseases through the computer. The computer helps us to simulate the disease, to mathematically replicate the disease. So the computer becomes sick of Parkinson. The computer becomes sick of Parkinson. So the model becomes sick of Parkinson. But I'm not going to go into the modeling. I just want to tell you at the end that one of the biggest challenges really is to deal with the human brain. So all that I told you came from understanding about mouse. Mouse is a wonderful lab animal because of many reasons. Also because there is a lot of similarities, and you should be aware that all the medication that you take were developed on the mouse. Most of them. Also on pigs. So these are the animals. But you cannot develop a medication directly on the human brain. But still, the human brain is not a mouse brain. So how do we deal with exploration of the human brain? And this is something new. I'm very proud of it that I'm the first Israeli to do it, and that's the following thing. You know that in operation, brain operation, you always take healthy pieces in order to go deep into, let's say, the tumor. So in this case, you have a tumor here, but you need to take a healthy piece here in order to get there. And this is a real piece that was taken in hospital of a good piece of the brain in order to go to the deep piece of the brain, epileptic region or tumor. So this is a living piece. It can live outside of the brain for 3 days, and you can do all the experiments you want because it's anyway being thrown to the, so to speak, garbage after the operation. They don't do anything with it. So we succeeded to convince a group of physicians now all over the world. So it's a beginning of a new era. Just to tell you how. So this is a mouse. This is the whole brain of the mouse to the same scale. So this is what we study, and this is what is being taken in hospital. For example, in Jerusalem, in Shaarei Tzedek or Hadassah, 3 times a week, you take this piece and you throw it. You don't use it. So we are starting to use it. I just want to show you that you also have brain cells, like in the mouse. So this is now a human piece, taken from the brain of a human. After operation, you can stain a cell, a nerve cell. You can reconstruct it fully in the computer. Now we have, for the first time, this is the first time, we see complete set of human cells reconstructed and living. These cells fire spikes. They are connected to each other with synapses. For 3 days, you can explore this tissue and learn something new about the human brain. So I want to tell you what is unique about your brain. We found, together with a Spanish guy, by the way, we are not going to understand the brain in Israel, but also not in Switzerland. We need a world collaboration, clearly. It's a challenge for the world. And so we need to collaborate now with the internet and all this, and I'm coming here, and tomorrow I'm going to Malaga, because in Malaga there is this group that are doing the Human Brain Project and so on. So I'm showing you a cell of a human with all its connection. And we know that we have much more connections between the cells. So one neuron talks to another neuron by much more connections. We are a connected brain, much more than any other animal. So this is one thing that makes us unique. There are other things that makes us unique. So we are starting to explore the uniqueness of the human cell. So already at the level of single cell, we are unique relative to the mouse. But there are also other things that together makes us unique. We don't understand all of it, but we can see that this genome change 200,000 years ago generated new brains, which are creative, which are aggressive, which have philosophy, which have science, and so forth. Finally, I want to show you what we also do. I think we have to prepare the next generation of young people, kids, to be prepared to the changes in the world. It's not going to be the same world in 20 years, completely not. Depending what Trump and others will do, but that's not what I mean. I'm talking about brain research and science. So we need to somehow present the brain to kids. So we are now developing a concept worldwide of having brain planetarium. I'm hoping that in Geneva Lake, along the lake, there will be posters explaining about the brain. Not only about this museum and not the museum, which is important, but the museum of the brain. We are now in Jerusalem in touch with all the 3,500 museums, science museums in the world, to have a corner for the brain. So every kid with his parents will come to study what is the brain. Why don't you sleep? Why are you afraid? What happens in your brain? And finally, we developed, and I really urge you to go home and look at it with your children or grandchildren, on Frontiers for Young Minds. This is a new journal in English now, but we are translating it to Hebrew, and we are going to do it in French, and then all over the world in Chinese. We don't need much money for that, but we do need some money for translation. We have the papers in English, about 120, with more than 1 million kids looking at it. And the idea here, it's a new journal, written by top scientists, but reviewed by kids. So we have kid reviewers. I myself wrote a paper and I was rejected twice by an American kid. I don't know, she's anonymous. I don't know who she is. I know she's 12. She said, Professor Segev, I don't understand what does it mean to stimulate the brain. There is already brain. Why do you need to put it in the computer? She was right. I had to explain it correctly. After two times she said, fine, I understood, it's in. So this is seriously, this is it's a kids journal written by top scientists, including Nobel laureates, reviewed by kids. So after the kids cross it, it will be good for your kids' brains, but also for your own brain. I learned a lot by reading the 120 papers that we already have. Can you replace seeing of a blind person with your ear? Can you see through the ear? The answer is yes. Amir Ahmedi in Jerusalem developed technology to replace vision by audition. Why do you sleep? There is a wonderful paper about the origin of sleep in your brain. What does Facebook do to your brain? We need to understand the brain. Activity in the brain of a musician in the motor system, which is only when he listens to music. Of course, there is an excess of activity in the auditory cortex of a musician. So there are particular regions of the brain of a musician that became overactive because of practice. And if you're an architect, there will be an overactive region in your visual system because you saw many details many times, and you develop a whole network that is expert in dealing with details. And if you're a taxi driver in London, which is a real investigation, because I don't know if you know, taxi drivers in London need to practice 3 years and remember all the huge number of streets and stores in London. They are really experts in GPS. They don't use GPS. They are not allowed to use GPS. Maybe now, yes. But when you scan the brain of a taxi driver in London, you see a big region in the hippocampus, which is a particular region that is increased in size because of new connections that are born in these taxi drivers, because they need to remember all these streets. So they need to generate maps, and these maps are generated by new connections. A new connection means bigger pieces, bigger part. So any expert has an enhanced region in order to deal with the particular demands of his or her own task. This is true also for animals. So here is an example of using MRI. MRI is magnetic resonance imaging just for scanning the structure. The fMRI is scanning the activity. So this is MRI of a musician in 3 different regions, in particular regions of the brain of a musician. You can see that an expert musician has an increased gray matter, increased connectivity, increased number of synapses and spines relative to non-musicians and relative to amateur musicians. So I'm sure that if I would scan Paul Coker's brain now, we shall get enhanced region, bigger region in the brain, in this particular region of the brain, in this particular other region. So you can see that there is an additional connections, an additional gray matter when you become an expert. What does it mean additional? I want to remind you again that we know today that when you learn something new, also now, I'm not saying that when you come from this auditorium, you'll weight your brain and it will become heavier. I'm not saying that. I'm saying that you have new connections, and these new connections enables you to remember, but if you become an expert, these many new connections makes this region somewhat bigger. They also have emotions, they are afraid, the mouse. But it's not highly connected. So music is not something that he likes very much emotionally. But we do. This is new scanners, so we have new scanners, and you can see how this is of human. So first of all, I want to tell you what makes us unique. I told you about connectivity within given cells, many connections per cell. Now I tell you that we have many connections between regions. No other animal that we know is so connected between one region to another region. We are very much connected. In other words, if you look at the human brain, it has a white matter. The white matter are the fibers. The gray matters are the cells. Most of our brain is white matter because of this connectivity, cross-regional connectivity. So when you hear music, it invokes many things, many associations, not only emotional, maybe visual, but also emotional, because the auditory system here is very strongly connected to the amygdala or other regions, which makes you feel. And this is a proof of concept. So these are, when you put a person in the magnet and you make him listen to music, you can see that emotional regions, I don't want to tell you all the names of these regions, this is thalamus and this is amygdala, this is thalamus, amygdala, subcortical region, and so forth. All of these regions are emotional regions. There are emotional regions, there are arousal regions, they are activated by music.